Hi, my name is Tim, and this is my partner Bryce. And today we're going to be doing a presentation on our Spotify recommendation system.
Our goals for the recommender system was to create a fast and effective Spotify recommendation system without requiring the use of user or song information. We found that this was best achieved through collaborative filtering and implicit feedback. For the dataset, we used the Spotify Million Playlist dataset. The neural networks were a little bit harder to train and more labor intensive. Because of how long they took to train, we were limited to using a subset of the Million Playlist dataset that consisted of about 2,500 playlists and about 130,000 unique songs. The pure matrix factorization, on the other hand, has pre-existing libraries that are very efficient and very easy to use. So we were able to train and test it using a subset that consisted of 15,000 playlists with 980,000 songs, 210,000 of those songs being unique.
So, the basis of all the models that we used is called matrix factorization. The way that it works is it factorizes the user song matrix that we created into two lower dimensional matrices, with the user matrix including factors that represent user preferences, such as the genres they like, and the song matrix includes factors which represent the song data, such as the artist that created the song, and etc. And then afterwards, we take the dot product of these two factored matrices to create a new matrix which fills in all the missing data in the process. So the different models that we use three different models for the neural networks and three different models for the pure matrix factorization. In order to test the model that we have, we split our data into training and testing data sets, and we performed a leave one out method where we would take one song from each playlist and create a list of 100 random songs, including the song that we took from the playlist. And then we would run the model on said playlist, and we would rank the lists of the random songs using the model. And we would check if the song left out of that playlist is within the top 10 recommendations of the random songs. Afterwards, we performed an NDCG calculation, which it's a type of scoring that gives much higher scores based on song rank. For example, it would give a very high ranking if the target song is within the top 3, but it would barely give any scores if the top song is, say, in like the 8th place.
The neural networks that I implemented, um, essentially, all of the neural network frameworks were based on a paper that is cited in the called neural collaborative filtering. That later, but first model from that was the general matrix factorization. Essentially, it just used PyTorch as a framework for factorizing the matrix. It consisted of embedding layers that created a dense representation of the input matrix that consisted of songs and users. And then it was able to generate basically latent features and train those using binary cross entropy loss. At the end, it went through a sigmoid function to squish it to a range of 0 to 1, probability of how much a user would enjoy a particular song. And the details of the training are there. Instead of using a simple dot product, it performs element-wise product of the user item latent vectors. These are fed into a multi-layer neural network to get a final prediction score. The goal of training is to reduce the point-wise loss between the predicted score and the next approach was multi-layer perceptron, which is more just your typical neural network. Again, it had individual embedding layers for user and song vectors. Those were then pushed through 4 fully connected layers with dropout and ReLU activation function. Again, sigmoid at the end, squish the range between 0 and 1. Training details are there. Uses the neural network architecture to try to learn about the interactions between the user and item latent feature. Because it employed nonlinearity with its activation function, it has a little bit larger level of flexibility than just pure matrix factorization, and having that tower structure allowed for learning of more abstract features. The final model from the paper, and probably the most novel one, was basically a combination of the two previous. Essentially, it would take the final layer right before the predictive layer, where it was squished into a final probability, and it would concatenate those two layers together and push them through a final output layer to do prediction. It benefits from pre-training because we can pre-train the general matrix factorization side and the multi-layer perceptron side, and that enabled this model to converge faster and have more stable results, as we'll see. And the training details are there. One thing of note is that we used a smaller learning rate for slower training just to really enjoy the benefits of the pre-training. And we get the best of both worlds because we get the linearity of the matrix factorization and the non-linearity of the deep neural network.
So for the three different pure matrix factorization models, I based it off of a library called Implicit, which cited three different studies for the different strategies that it employed. The first one was the logistic matrix factorization, which is a strategy that assumes that all zero user interaction is a negative interaction, meaning if the user hasn't listened to the song, they don't like it. And this is specifically optimized for the mean percentage ranking, which will give higher rate to recommended songs with more listens, which definitely shows its dependence on the highly variable data that it needs. And this model also allows for the cosine similarities and other nearest neighbor models, although it's not as optimized for that type of applications as the other ones are. And the way this strategy works is it's like normal matrix factorization, but it also further splits the user song matrix into smaller blocks of k times l size. And it uses an alternating gradient descent strategy similar to the alternating least squares. And due to the splitting of the user song matrix, it allows us to save on memory and perform parallelization, which allows us to have a faster runtime overall. The next strategy is the Bayesian personalized ranking, which randomizes zero user interaction as missing or negative interactions. And this is specifically highly optimized for area under the curve scoring, which is scoring that linearly scores the song by its rank. So it'll gain the same amount of points as it would going from the third place to the second place as it does going from, say, the 8th place to the 7th place. And ideally, it would have a data set of negative and positive interactions, so it wouldn't need to do the randomization. The specific strategy for this is it splits the user song matrix into item pairs instead of just a user vector and a song vector, and then it optimizes for the ranking of the item pairs rather than just the individual items, which allows us to have the similarity scoring for the use of nearest neighbor models. This uses a stochastic gradient descent algorithm, and it also means that it'll be slower for dense users and song matrices. The last strategy used is the alternating least squares, which would require an ideal data set that is binary with user interaction and non-interaction, which is what we have. And this strategy is optimized for NDCG scoring, and the way that it does the optimization is it alternates between minimizing the weighted root mean squared error score for the user and then the song factors, which guarantees the lowering of the cost function.
So we're just going to go over some of the accuracy curves and the results for the neural network approaches. Here we have the curve for the general matrix factorization, the multi-layer perceptron, and the neural matrix factorization. As I'm sure you can see, the curves are quite noisy, and that's just due to limitations in the validation step. Since the training data was so large, it just wasn't realistic to have a validation set that was even 1%, as it would make the time to train totally unrealistic. And we already mentioned how we trained using only 100 out of the 130,000 total. So that accounts for the large spikes and drops in the performance between epochs. And then this is just the average performance over all the epochs. You can kind of see with the hit rate, it's sort of what you would expect, that it improves between the more simple models and the pre-trained neural matrix factorization model.
So going over the pure matrix factorization results, this is the logistic matrix factorization. One thing to note is that this model doesn't actually work with the NDCG scoring, just because it relies on having a negative confidence score or negative prediction score for the song, which means that it won't be able to be used for the NDCG. This is for the Bayesian personalized ranking. You can see that it has a high hit rate and kind of middle NDCG score. That's because it's more designed for AUC scoring instead of NDCG. And this is for the alternating least squares, which unsurprisingly has both a really good hit rate and a really good NDCG scoring. And this is just a comparison of all the hits and a comparison of all the. This is the table. As you can see, the Bayesian personalized ranking actually has a higher hit rate than ALS, but it kind of suffers in the NDCG portion, getting nearly half of what ALS had for it.
The sort of qualitative, subjective results, where we're just going to show some samples of recommendations. So at the top, we have the playlist that was inputted, and then below, we have the recommendations for each model. You can just sort of glance over them and see if they make sense to you.
It's the same for the pure matrix factorization, although I was able to incorporate the Spotify API for it. Sadly, the Spotify API is only limited to doing recommendations up to 5 songs. Therefore, the comparison isn't necessarily as accurate as it could possibly be. One thing to note about this specific qualitative test is you can see that the Bayesian personalized recommendation was able to recommend songs within the same era of the 80s and 90s, but it doesn't necessarily recommend songs of the same genre, unlike ALS, which was able to recommend both the same genre and the same era. And on the other hand, for a playlist filled with more niche / unpopular songs, such as classical or instrumental songs, we see that the Bayesian personalized ranking actually does a lot better in this one, recommending songs that are only purely instrumental. Meanwhile, alternating least squares was able to recommend songs that were slow and somber and kind of instrumental, but it still had lyrics in them.
Our sort of how we think that everything performed. The alternating least squares seems to have performed best because it is less subject to sensitivities based on the size of the playlist. And actually, that's not surprising because the paper that the neural collaborative filtering was all based off of, they used alternating least squares as a comparison, citing it as at the time state of the art. So it's unsurprising. And the rest of them are actually also not terribly surprising because of the simplicity of the models.
So the conclusions that we came out of this project is that the logistic matrix factorization is actually unsuited for the use of binary dataset, which is unsurprising because that's what they said in the paper they cited. And what we saw with all of the models that we had was that collaborative filtering suffers from a cold start issue where it would have a hard time recommending the proper songs if the playlist that we feed into the model is sparse and only contain a few songs. And this could be addressed with the integration of content-based filtering, such as using the song data to recommend to other songs. And we noticed that the high hit rate of the BPR is indicative of its performance for more niche and unpopular genres, as seen from the qualitative test earlier. And the high NDCG score of NMF and ALS is indicative of its song recommendations having high rankings for the user and more factors to be able to pull out for the songs that are being recommended. These are our references. Thank you for listening to our presentation.